In this video, we're going to go over page 2 of the note pack on the rational functions. And yesterday, or in the previous video, we looked at the page 1, and we saw the impact if we had a graph that looks like 3x minus 7 over x minus 2, and saw that that created a function that looked much like the y equals 1 over x graph. Today we're going to look at some graphs that are quite different from the 1 over x graph. They're also called rational functions, a rational function being a function that has a polynomial in the numerator and a polynomial in the denominator. So number 3, we have to find the horizontal and vertical asymptotes of the function x squared plus 2 over x squared plus 1. Now we know it's not algebraically sound to cancel these x squareds out and say this expression is equal to 2. That would definitely be a big problem to try to reduce that graph like that. So this function is a rational function, again, because it has a polynomial of degree 2 on top and a polynomial of degree 2 on the bottom. And to begin with, I will usually ask you to rewrite your fractional rational equation into a form from doing the division. So we're going to start out dividing the x squared plus 1 into the x squared plus 2. This will help us see the asymptotes quite well, particularly the horizontal asymptote. And so I know that x squared times 1 will give me x squared. Just goes into there one time. I do my subtraction, and when I do that, I get a remainder of 1. But just like in the previous video, when we rewrite our expression of little f of x, I'm not going to write this with a remainder of 1. I'm going to use the fractional equivalent as far as its remainder. So f of x is equivalent to 1 plus 1 over the divisor x squared plus 1. Now, when I have it in this form, it's very nice to be able to see that this is related somewhat to that 1 over x graph, and I can see that the horizontal asymptote is going to be made available to me upon doing that division. So let's look at the asymptotes and the intercepts as I asked you to find. So we need to find vertical asymptotes and we need to find horizontal asymptotes. Now, a vertical asymptote will come about once I look at the fraction and find out what causes my denominator of my fraction to turn to 0. So in a rational function, values after this function has been reduced down, values that cause your denominator to turn to 0 will actually look like vertical asymptotes in your graph. Now, x squared plus 1 is never going to equal 0. So I'm never going to have an input that's going to cause me to get a vertical asymptote. Had this been x squared minus 1, I would have been able to input 1 or negative 1 to make the denominator turn to 0 and have an undefined fraction. And that would have caused me to have a couple of vertical asymptotes actually. However, when this is x squared plus 1, this denominator can never be smaller than 1. Therefore, vertical asymptote-wise, I don't have any. So sometimes we can have rational functions that don't have any vertical asymptotes. Up to this point, we hadn't seen that. Now, horizontal asymptote-wise, this fraction, as I let x become larger and larger and larger in the positive direction, this fraction will actually become teeny tiny. 1 over a very, very big number. Say I put in 1,000,000 for x, and I square it, add on 1. 1 divided by 1,000,000 squared plus 1 is going to be very close to 0. So the y-coordinate can approach this value, this integer here of 1, but it's never going to actually be able to be that value. Therefore, I will have a horizontal asymptote at the line y equals 0. So I have no vertical asymptote, but I will have a horizontal asymptote at y equals 0. The end behavior of the function as x gets larger and larger and larger in the positive direction, and I wrote this wrong, it's going to be 1, not 0. The end behavior of this function as x gets bigger and bigger and bigger is that this fraction is going to get smaller and smaller and smaller, get close to 0, which means that 0 plus 1 will be a 1 value. So horizontally, this graph will keep having an end behavior that's closer and closer to 1 in the positive direction, as will it be in the negative direction. If I put in very small numbers, negative 1 million, negative 1 billion, it's going to get squared, add on 1, and this fractional part will turn closer and closer to 0, which will cause the y-coordinate to get very close to 1, although it will never get there. So y equals 1 is going to be my horizontal asymptote. Now, the intercepts I asked about. For the x-intercept, we know that x-intercept-wise, we're looking where does the y-coordinate equal 0. And we find out for our x-intercept, I'll use this original, or I can use this other form. When does the y-coordinate equal 0? Again, if I multiply both sides by x squared plus 1, I get 0 is equal to x squared plus 2. And x squared equals negative 2. And I'm going to find out that there aren't any x-intercepts in the real number system anyway. We could use complex numbers, but those wouldn't be available. I wouldn't see them on my Cartesian coordinate system. So there are none for x-intercept. On the other hand, if I wanted to look at where I have y-intercept, the y-intercept or y-intercepts are going to occur when I plug 0 in place of x, and what do I get for y? And if I go back to the original function, if I plug in 0 for x, I find out that I'm going to have a y-intercept at 2. So at the point 0, 2, we will have a point on our graph. Now, this graph, if I just draw a little sketch, I know I have a horizontal asymptote at y equals 1, so this is at 1. I know I have a y-intercept at 2. And I know there are no x-intercepts. We already established that here. And in fact, this graph is always going to be above the line y equals 1, because this function is equivalent to 1 plus a little bit. And this function keeps getting closer and closer to 0, this part of the function keeps getting closer to 0 as x gets larger and larger, meaning the sum of these two keeps getting closer to 1. If we plotted a few points, we'd find out that the graph actually looks something like this. Very different from the two graphs that we did on the previous page. So depending on how the graph looks, how the rational function is set up, it can look like a hyperbola, it can look like kind of a bell-shaped curve here, and there are many other ways that rational functions can look. They have lots of different forms they can take on. Let's look at number 4. So k of x, we're going to identify where the asymptotes are and the intercepts, and make a little sketch of the graph. Okay, once again, I'm going to start out doing the same thing we've done on each of these rational functions. I'm going to do a division. This is going to help me see where my horizontal asymptote is, possibly, or possibly some other type of asymptote. And they're kind of going a little crazy with that division mark there. All right, so we're going to divide. Now, I have these missing placeholders here, so we'll quick put those in. And I find out that x squared goes into x cubed x times. And multiply. Line things up appropriately. And subtract. And I don't have anything else to bring down. So therefore, I get my k of x function is looking like this. When I do my longhand division, I know that the x squared minus 9 goes into my function x times with a remainder of 9x over x squared minus 9. Now, in the other divisions that we had done previously, we always got an integer that was here, not a variable expression. Well, let's see what the meaning of that is. We want to identify where do we have vertical asymptotes? Where do we have horizontal asymptotes? And then we're going to have something new that's called a slant asymptote. And naturally I'm bringing that up because we have one here. Now the vertical asymptotes, remember, will come about from what makes your reduced form of your denominator turn to 0. And I can see that this denominator of this fractional part would factor to x plus 3, x minus 3, or I know that x equals 3 and x equals negative 3 will cause me to have undefined denominators. So those are the equations for my vertical asymptotes. I'm going to actually start to make a little sketch over here right while I find these values. So at x equals 3 and at x equals negative 3, I have some vertical asymptotes. Now, horizontal asymptotes occur as I let n behavior, look at the n behavior. And as I let x get bigger and bigger and bigger, this denominator actually dominates the fraction. And this fraction will keep getting closer to 0. Even because there's an x up here, it will still keep getting closer to 0 because the squaring of that denominator will actually cause the domination to have the denominator get bigger, way bigger, faster than what the numerator does. So this fractional part will actually go to 0, but my function then is not going to keep getting closer to a specific single number as it did up here. It's going to keep getting closer to this variable expression. So here I actually have no horizontal asymptote, but I have my graph is going to keep getting closer and closer to the x-coordinate of my input. So I do have all asymptotes are going to be equations of lines, and I have a horizontal asymptote at y equals x. So if this division yields a variable expression, you're going to have a slant asymptote. And interestingly enough, your slant asymptote doesn't actually just have to be a line. It's possible you divide this and you get a square here, or a quadratic, or a cubic function. So there are all kinds of interesting slant asymptotes that can come about. We'll use the simpler ones, but you can get very, very complicated functions. Now I'm going to sketch in my slant asymptote. I know how the y equals x looks, which again, this is kind of crazy. We hadn't had this type of a graph before. And now I have to find where my x-intercepts and y-intercepts are. My x-intercept is going to occur, once again, when I want to figure what input gives me an output of 0. I'm going to go back to that original fraction form. That's usually easiest to do. And multiply both sides by x squared minus 9. I get 0 is equal to x cubed. Therefore, I get x is 0. And so I'm going to have an x-intercept right here at a 0. And lo and behold, that's where my y-intercept is going to take place too. I mean, I would find it differently, but it's going to end up being the same value. For the y-intercept, I'm thinking again, what y value gives me, what y value I get when I plug 0 in place of x. Alright, so I have a y-intercept of 0 and an x-intercept of 0 because my graph goes through the point 0, 0. Now, with that much information, it is quite difficult to tell how the graph is going to go. I would need to plot some more points, and I've done that ahead of time, and I'm going to just sketch in just for time's sake. But I would have to plug in a couple points, say plug in -1 into my k of x function, plug in -2 or 2, it gets a few values. But the function actually graphs like so, and I would only get that by plotting points. I can't just look at this and tell that this swirling effect is going to take place. Same thing is true with the rest of the graph. We know you can plug in values that are bigger than 3 and less than negative 3, but how do I graph those points? These asymptotes are going to somehow guide me, and I would basically have to be plotting some points to figure out how to graph the rest of the graph. And once I plot in some points and say I plug in 4, if I plug 4 in here, I have plug 4 in, I get 64 over, and I get 16 minus 9, and getting a decimal approximation for that, 64 divided by 7, that comes out to be about a little bit bigger than 9. So I would actually have a point that's way up here. This is at 3, so roughly up here. And as I would plot more points, I would actually find that my graph would be contained inside here. And likewise, if I plot some points over here and plug in -4 and -5 and -6, etc., I'll find that this asymptote is causing this graph to stay confined within these two branches of this slant asymptote and the vertical asymptote. So rational functions have many, many different ways that they can come about. We noticed on the front side that you could have the typical hyperbola. You can have a graph that looks bell-shaped. You can have some slant asymptotes that cause you to really have some crazy behavior. We have vertical asymptotes, no horizontal, and some slant asymptotes. We will find as we do some trends as we start to look at more of the graphs and be able to make some generalizations about what is going on. So right now we'll just go through 3 and 4, and we'll leave 5 for a later time.